That's a big error that many students make, is they're so worried about the differentiability on the endpoints, and we don't care about the differential of the endpoints. Hello everybody there, welcome to Cranky Calculus. Do not forget to like and subscribe, and we're going to be talking about the mean value theorem here. Don't forget that we do have the free notes down below in the description, so check that out, and let's get rocking and rolling here. About the mean value theorem today, but first off, we're going to talk about Rolle's theorem, which is actually corollary of the mean value theorem. Rolle's theorem says this, and you can see how it's got three hypotheses there, and I'll draw some pictures as well so that it makes some sense for you here. If you have any 2 points that are of the same height, so let's pretend that these two dots right here are of the same height. In order to connect those, as long as connect those two dots with a curve that is continuous and differentiable, then there will always be at least one slope that is zero. So if I just connect those two dots in just that way, I'll always have at least two slopes. Look right there, I have a slope that's zero in blue, and I have another slope that's in blue that's at zero. So that's what Rolle's theorem essentially says. As long as the endpoints are the same height and we can connect the two dots, we're continuous or differentiable, we guarantee that the derivative will equal zero at least one time in that. So let's go with this example right here. Verify that the function satisfies the three hypotheses of Rolle's theorem on the given interval, and then find all numbers C that satisfy conclusion of Rolle's theorem. So here we go. So first off, we are going to be continuous because this is a polynomial. So f is continuous on the interval from -1 to 1. It's actually continuous everywhere. Since this is a polynomial, f is also differentiable. And this is going to happen inside of -1 to 1. That's just going off the definition. We need to be continuous on the entire interval, but we don't need to be differentiable inside the interval. I'll zoom in here so my handwriting isn't quite as bad. We just need to check the endpoints there. So my endpoints are going to be -1, so f of -1 needs to equal f of 1. So real quickly in my head, I'm going to do this. I believe I get a -2 here if I plug in a -1. So I'm going to get -2. And hopefully that does equal f of 1. And I'll plug that again in my head here. And I'm going to get a -2. Yeah, -2. So we're good to go. So all hypotheses are met here. So now what we need to do is we need to go ahead and solve for Rolle's theorem. So we're going to find the derivative here. So f prime of x is equal to 3x squared plus 6x minus 1. And we're going to set this equal to 0. This is something that I cannot factor. I can just look at it and just tell. So I'm going to use the quadratic formula here. So x is going to equal -b, which is 6, plus or minus square root of b squared, which is going to be 36, minus 4ac, that's going to be minus 12, all over 2a, which is going to be 6. By the way, that's root 24, which is the same thing as 2 root 6. So this is x is actually equal to -1. I'm just going to split this up into two ratios here. Well, so we're at -6/6, that's just 1, or -1 rather, plus or minus root 6 over 3. Okay? So as I go through this and I'm looking, you're going to see here that we're going to see what graduates to be a C value here because we need to be inside the interval from -1 to 1. And if you look here at -1, if we subtract another value from -1, that's not going to be in there. So the only C value that's going to graduate is -1 plus root 6 over 3. We reject the negative because it is outside of our bounds. So this is going to wrap up our problem here for Rolle's theorem. Rolle's theorem works for this right here, and we are capable of finding our C value where this does happen. Up here, we're going to actually talk about the actual mean value theorem here, and this only has two parts of the hypotheses. As long as f is continuous on the closed interval, differentiable inside, that's important to know that it's inside the closed interval, then there is some number c such that the derivative of f is equal to the secant. So really what this means, if I can translate this for you, I'm going to zoom in. If I have 2 points of any height, so there's just 2 points of any height. If I were to connect those 2 points, as long as I'm differentiable, continuous as I connect those points, whatever, if you can see the slope of this dashed line right there, the slope of that dashed line is actually going to be tangent to at least 1 point. So I can see that that's going to actually happen right here. So those slopes will be parallel. So the slope of the secant line is the slope of the tangent line, at least in one spot with our graph. So that's what that says. So let's go ahead and use MVT here in the first example. Let f of x equal x squared minus 2x on the interval from -1 to 2. Verify that we can use the mean value theorem, and let's find that number c that satisfies the conclusion. So the first step I'm going to do here is I'll zoom in so my handwriting isn't so bad. This is another parabola, so like we're totally good to go here on continuity and differentiability. So f is continuous on -1 to 2. And f is differentiable. So this is me verifying that we can use it. Again, this is a polynomial. I can't talk and write things differentiable. I hope that's spelled correctly. All polynomials are continuous and differentiable everywhere. If I had a ratio, or if I had some type of maybe square root or exponential function, anything that might be a little bit weirder, we might need to actually show it. But for polynomials, we're good to go because we know it. If you know that's continuous, that's good enough for me. The only time you need to show the continuity is if you have a piecewise function. That's really the big ones we got to show. Piecewise function, or if we have word problems where we're given differentiability. Other than that, we're pretty much good here. So now let's go ahead and satisfy MVT. So let's go ahead and find what f of 2 is minus f of -1 all over 2 minus -1. So that's going to give me a 3 in the bottom here. F of 2 is going to be 4. That's going to be 0. 4 minus 4 minus, it's going to give me 1 plus 2, so 3. This is going to equal -1. So I'm going to find f prime now of x, which is going to be 2x minus 2, and I'm going to set that equal to -1. Okay, I'm going to solve for this x now, so I'm going to get 2x equals 1, because I'm going to add 2 to both sides, and then so x is equal to 1/2. 1/2 is inside my interval from -1 to 2, so that graduates to a c value. So there we go. So here's our c value that satisfies MVT. Now, sometimes we're just only asked to verify whether MVT is capable of being used. Very common, and the trick here is this differentiable inside the interval. As long as we are differentiable inside the interval, not on the interval, we're good to go. So for this one right here, this is one of those weird functions I was talking about earlier, where we can't just guarantee that we're going to have some type of continuity. So we do want to look at it, be able to solve for it, and hopefully you know what a question or what these functions look like. All these fractional exponents, as I call them, they all have two different looks. They either look like a bird, or they look like this. So, and then so that's an odd one right there. So x to the 3/5 will kind of look like what I have there. The other one that I see a lot is this one, the one that looks like a bird, and that's going to be a if the numerator is even. So any numerator that's odd, it's going to look like the first one. Numerator that's even will look like the second one. So this is continuous. There is no x value that's limited. The continuity stuff is going to get messed up again with a piecewise function or a ratio where we might have holes and vertical asymptotes. But other than that, f is continuous on this interval. Differentiable is a different story. We actually have to work this one out. So let's go ahead and find f prime of x. That's going to give me 3/5 x to the -2/5. If you know how to rewrite that with your algebra, it gets a little bit easier because we can do 3/5 x to the 2/5 on the bottom. And why I think it's easier to do that is we can tell that x cannot equal 0 for the derivative. Okay, so we're not differentiable. I can't even spell differentiable. I'll just do diff. Not differentiable at x equals 0. 0 is in this interval, so cannot use MVT. And we can say because x equals 0 is inside the interval -1. Oh, you know what? I need to do open brackets on that one. -1 to 1. Okay? moving on here to our last problem. Again, we're going to be trying to verify the hypothesis for MVT here. This one's going to be continuous here. I'm going to do this one in blue, so F is continuous. The differentiability one, oh, that's going to be on. I'll write this all correctly. The differentiability one is going to be a little bit tight, just like it was for the last one. If I'm doing this, I'm going to get x to the -3 halves, -2/3, if I could get my dyslexia in order. So I'm going to go ahead and get this. The derivative is 1 over x to the 2/3, which means that x cannot equal 0 for the derivative. So does MVT apply? Yeah, it does, because 0 is inside between open parentheses of 0 and 8. So we can use MVT because x equals 0 is not inside of 0 and 8. So essentially is we can use MVT if we're not differentiable on the endpoints. It does not matter to us. We only care about if we're differentiable inside. That's a big error that many students make, is they're so worried about the differentiability on the endpoints, and we don't care about the differential of the endpoints. We care about the continuity on the endpoints. We care about the differentiability in between the endpoints. And that's going to wrap up our video here. Do not forget to like and subscribe.